Hello everyone, welcome to Simplified Triple Studies. In this session, I'll be discussing analysis of AC through RL series circuit. Let's get understand the fundamentals of RLC series circuit. It's very important for all the branches of engineering. First of all, I'll ask one question. What do you mean by RLC series circuit? So we have three elements such as R, then L and C which are connected in series. Okay, and a supply voltage, an AC voltage is applied across RLC elements, and the value of resistance that will be in terms of ohms, and the inductance value that is in terms of Henry, and the capacitor value that is in terms of farads. So we are considering ideal condition. Okay. You know that it's a series circuit, so the same current flows through each and every element, but the voltage is getting divided. Voltage across resistor, voltage across inductor, and the voltage across capacitor are getting totally different. So same current and voltage will be different. That is a speciality of RLC series circuit. This arrangement is known as series RLC circuit. Let me take you to the circuit diagram of series RLC circuit. We are having resistive element, inductive element and the capacitive element. All are connected in series, or you can call it as cascade. And a voltage V is equal to Vm sin omega t. It is a Vm is the peak value and omega is the angular frequency. And this is your total voltage V. And VR is the voltage across resistor that you can able to calculate using the formula I into R, where VL is the voltage across inductor. It can be computed by using the formula I into XL, where XL is known as inductive reactance. You can calculate inductive reactance by using the value of inductance and the angular frequency. You have to multiply both L omega. And if I talk about the voltage across capacitor VC, you can easily calculate by using the formula VC is equal to I into XC, where XC is known as capacitive reactance. So XC can be computed using the formula X is equal to 1 by C omega. This concept I already covered. Okay, this is just for your information. Just understand the circuit diagram. Now one more speciality I want to tell you, that regarding the resistor, voltage across resistor and the current through the resistor both are in the same phase. There is no phase angle difference between the current through the resistor and the voltage across the inductor. If I talk about the inductive voltage and current through the inductor, the scenario will be like this. So you can take the current as a reference here. Then what about the voltage across inductor? Voltage across inductor leads by the current at an angle of 90 degree. Why 90 degree? Because it's an ideal condition. I hope you are understanding. If I talk about the voltage and the current through the capacitor, so let me draw the current as a reference. Then how can I mark the voltage across capacitor? See, voltage across the capacitor lags behind the current at an angle of 90 degree if and only if the things are ideal. Okay, like this you can able to mark. This is your VC. Okay, 90 degree. So this concept also you have to remember. So if you know this concept, then it is very easy to calculate impedance, phasor diagram, and then phase angle, etc. Now, first in the foremost, we need to consider a condition such that here the inductive voltage greater than capacitive voltage. I mean voltage across inductor greater than voltage across capacitor. So obviously VL greater than VC. Therefore, the entire circuit will behave as a inductive circuit. Is it okay? Therefore, let us consider the particular phasor diagram. In the foremost, you can draw the current as a reference. Then you can mark the voltage across resistor as VR. Okay. Then you can talk about inductive voltage across inductor. This is your voltage across inductor VL, and you can mark the voltage across capacitor. This will be VC. I already explained. Now you can able to say that we are assuming that inductive voltage greater than capacitive voltage. So therefore you can say that this is your the difference in voltage between inductor and capacitor voltage. So you can mark it as VL minus VC, because inductor voltage is greater than capacitor voltage here. Voltage across inductor greater than voltage across capacitor. So let me mark like this. So what about the resultant voltage? Resultant voltage will be in this fashion. This is your resultant voltage V. Okay. So you can able to complete the particular segments, and this will be obviously the same figure. So this will be VL minus VC, and this is your resultant voltage. This will be VR. Like that I have drawn here. Please have a look on this. Current is here. This is your voltage across resistor, and the base side will be VR. VR will be the base side. VR is equal to I into R. Then hypotenuse should be the resultant voltage V. Then the height will be the difference between VL and VC. That is written as VL minus VC. So everybody please have a look on this. Okay, this triangle is very essential for us. How did you get this triangle? You can able to imagine. So suppose if I take about, if I consider capacitor voltage greater than inductor voltage, then diagram comes down, that you can able to draw. I hope it is very clear. So please consider the triangle VR equal to IR, then VL minus VC, then V is equal to IZ, where Z is the impedance. Okay, this is the first condition you have to consider. This is your phasor diagram. Okay, please understand how to draw the phasor diagram. Then you have to calculate the impedance. Now do one thing, please consider the right angle triangle. Okay, then hypotenuse you have to identify. This is your hypotenuse, then you have the base, then this is your height. Apply the Pythagoras theorem. V is equal to square root of VR square plus VL minus VC the whole square. VR means I into R, VL means I into IL, VC means I into XC. Please substitute accordingly. Current can be taken as outside. Therefore, current can be written as voltage by square root of R square plus XL minus XC the whole square, where you can call impedance equal to R square plus XL minus XC the whole square. This is your impedance, which will be expressed in terms of ohm. Okay, this is the way how to calculate impedance. Now I will be discussing how do you calculate the phase angle. For calculating the phase angle also we require the same phasor diagram. So please consider the triangle everyone. Now from this you can calculate the tan phi. What is tan phi? Opposite side by adjacent side. So we have the VL minus VC will be the opposite side and VR will be the adjacent side. So VL minus VR. So VL can be written as I into XL, VC means I into XC, VR means I into R. Therefore current term will be getting cancelled. Same term is repeated at numerator and denominator. Ultimately we are able to get XL minus XC by R. From this you can compute the phase angle taking the tan inverse. If I take the tan inverse, I am able to get the equation as tan inverse of XL minus XC by R. So this is your phase angle. I hope it is clear. Now you have to calculate the power consumed in total power consumed in RLC series circuit will be VI cos phi. So you know that cos phi will be R by Z. So VI into, you can write R by Z. Okay, R by Z. You can able to write like this, cos phi means R by Z, or else I can write it as I square into R, I square into R. So power factor means cos phi. Okay, cos phi means I square, so power factor, therefore power is equal to VI cos phi, that is equal to I square into R. So this much of amount of energy will be dissipated in the form of heat. Okay, now how do you calculate the power factor? For calculating power factor also we require the same triangle. So cos phi means adjacent side by hypotenuse, no? Adjacent side by hypotenuse. What is adjacent side? VR. VR means I into R. Hypotenuse means V. I into Z. I and I will be getting cancelled, therefore divided by Z. This is your power factor. There are three cases which will be existing in case of RLC series circuit. The first case is greater than XC. Such case we can able to say that phase angle is positive. Then we can able to say that the current lags behind the applied voltage. Therefore power factor is lagging. The second case says that XL less than XC. Such case the phase angle is negative. Therefore we can able to say that in that particular circuit the current leads the voltage at an angle of 90 degree. In the third case, XL, if XL equal to XC, we can able to say that power factor is equal to 0. If power factor is equal to 0, therefore we can take cos 0 is equal to 1. So we are able to get unity power factor. You can able to go through these different cases. This will be really helpful for competitive examination. And I have drawn some diagrams related to that. The first case we can able to say that the phi is lagging. The second case phi is leading, and third case the phi is equal to 0. These are the three respective cases you have to understand. And what are the major applications of RLC circuits? You can use it for tune circuit, filter, then oscillator and a pulse discharge circuit. These are the various applications.